What if I told you that understanding this one physics principle could actually help you lift a car with your finger? Today, we'll be tackling a multi-stage hydraulic system problem, which is on the particle model of matter. So, this is the channel that breaks down all of those topics that you might be having issues with into bite-sized, understandable strategies. And then if you have questions, feel free to just drop it down in the comments. And remember to like, subscribe, and share so that once we drop a new video, you'll be the first one to be notified. So let's jump right into it. Now, this particular problem showcases real-world hydraulic engineering, and it's designed to help you put all that you have learned on the particle model into practice. So we'll be dealing with some practical problems here. Now, this is a 3-stage hydraulic system that needs to lift 45,000 newtons. That's roughly the weight of a small car. So feel free to pause this video, right, and then go through the questions. Now, look at this setup. You've got 3 cylinders all connected by hydraulic oil. Cylinder A is pretty tiny, cylinder C is massive, and that is cylinder B sitting in the middle. All right, so we've got specific areas, we've got the oil density, we've got the depth, and all of the values we've been given in the question. They're pretty important. So before we dive in, grab a pen and paper, pause if you need to do, and let's solve this together. All right, so the first part of the question asks us to find the pressure needed at cylinder A to lift that 45 Newton load. Now, here is where many students go wrong. They overthink the entire situation. Now, the key insight to this problem is called Pascal's principle, which states that pressure applied anywhere in a closed fluid system gets transmitted equally throughout. That means the pressure in cylinder A equals the pressure in cylinder B. So we start with cylinder C. Pressure equals force divided by the area. That's 45,000 newtons divided by 0.80 square meters. That gives us 56,2050 pascals. Easy, right? Now, part B is all about conservation of volume. When cylinder A moves down about 0.25 meters, where does all that oil go? It can't just disappear. It has to push up cylinder C, right? So first we calculate the volume displaced by cylinder A, area times distance, that is 0.02 square meters times 0.25 meters. That equals 0.005 meters cubed. That's the same volume. That same volume must appear in cylinder C. So distance equals volume divided by area, 0.005 cubic meters divided by 0.80 square meters. That gives us 0.00625 meters. So notice how small the cylinder moves a huge distance, but the large cylinder just barely moves. That's the trade-off in the hydraulic process. You gain first, but you lose distance. Right. Okay. The part C of the question tests your understanding of the pressure in liquids. And we need additional pressure from that 2.5 column of oil in cylinder B. The formula is P equals the height multiplied by rho times G. Okay, so the depth given to us from the question is 2.5 meters, and then we multiply that by 850 kilogram per meters cubed. That is our density, our rho, multiplied by 9.8 Newton per kilogram. Now, if you use G equals 10 instead of 9.8, you get a similar answer, a perfect level of approximation. Always use 9.8 except stated otherwise by the question. All right. And then the last part of the question, we should explain. Part D is where deep physics understanding really shows. It's asking us why the mechanical advantage isn't simply the ratio of areas. Now, here's the key insight. Energy cannot be created or destroyed. Remember that from your law of conservation of energy, right? So, if cylinder A moves down a large distance with small force, cylinder C will move up a tiny distance with a pretty huge force. So, the work done must be equal. Plus, that intermediate cylinder B, it's just transmitting pressure. It doesn't multiply your mechanical advantage. Now, and in real systems, you lose energy to friction and or compression. Plus, that intermediate cylinder B is just transmitting pressure. It doesn't multiply your mechanical advantage. And in real systems, you lose energy to friction and or compression. So you need to consider all of those multiple factors: energy conservation, the role of intermediate components, and real world efficiency losses. So before we wrap up, here are the top tips for tackling this kind of problem. Number 1, always start with Pascal's principle. Pressure is the same throughout. We've talked about that earlier. Number 2, watch your units. Convert everything to standard SI unit before you launch into your calculation. Number 3, for conceptual questions like question D, think about energy. Physics loves energy conservation principles. And then number 4, show your workings. Clear step-by-step solutions help you catch errors when they occur. And, it will show that you really understand what you're doing.